Hello, section 7. There we go. Recording from home again today. So let's see. Screen shares seem to come out a little clearer than putting the hand out in front of the webcam, so I thought I'd do it that way. So instead of pointing with my finger, I've got the little cursor here. Section 7 starts out with Newton's third law. Like it says here, if A exerts force on B, then B exerts an equal and opposite force on A. Forces always come in pairs, is the idea, because the things that are exerting the forces always come in pairs. You'll never be walking down the hall late one afternoon and you get knocked over on your face, and when you turn around to say something, nobody's there. That would be kind of creepy. If you get pushed, somebody has to do the pushing. There's two bodies involved, and always, not just with collisions in hallways, any kind of force. And what the third law says is that this is always a mutual interaction. Not only did the other person push against you, but you were simultaneously pushing back on them, and the forces are the same size, okay? If the force that pushed against you was 45 pounds, you were simultaneously pushing the other person with a force of 45 pounds. The reason you fell over and the other person didn't is because you were just not as well balanced, or the other person was braced better for it, or something like that. But anyhow, anytime there's forces, it's two objects pushing or pulling on each other. And that phrase, on each other, kind of is what the third law is all about. It's worth keeping in mind. So they're called an action-reaction pair. The two forces are, for every action, there's an equal and opposite reaction. Once in a while, somebody asks me, how do you know which one is the action and which one is the reaction? Well, the action is just whichever one you happen to look at first, and the reaction is the other one. It's not like one occurs before the other or anything. They're simultaneous. So a few examples. Here we see somebody's badly drawn foot pushing against a ball while you are in the act of kicking it. At the same time that you're pushing against the ball is pushing back on you, which you may or may not be aware of, but if you kicked it barefoot, you'd probably feel the ball slapping your foot while you were doing it. Maybe a better illustration is if kicking a ball while standing on a skateboard would be kind of tricky. Maybe throwing a ball would be a better way to think of it. But if you were in some nearly frictionless situation, like standing on a skateboard or sitting in a canoe in the middle of a lake, and you threw some heavy object, you would start to go the other way, okay? If you throw the ball forward, you're going to start to move backward, because the action propels the ball in one direction and the reaction propels you the other way. Kicking a soccer ball in the middle of a grassy field, there's a friction force on your other foot that cancels out the reaction force on this foot, and so you don't go anywhere. But take away that friction and it becomes pretty clear that it's a force in each direction. Well, a few more examples. You've got a box sitting in an elevator, or it could be a person. It's just boxes are so much easier to draw. So A is the force of the box pushing down on the floor, and B is the force of the floor pushing back up on the box. So box pushes on floor, floor pushes on box. That's the kind of thing that the third law is talking about. A and B would be the box and the floor here. A exerts force on B, B exerts force on A. So this is an example of an action-reaction pair. That means they are equal to each other in magnitude. If one of them is 15 pounds, the other one's 15 pounds. Now, the thing here that might be a little tricky is it says the elevator is accelerating. And I think there was an example like this earlier. If there wasn't, there probably should have been. But here, let me. There's the floor. There's the box. If you want to compare the weight of the box to, oh, did I call it A or B? B is the one from the floor on the box, okay? And it says the elevator is accelerating. Okay, the elevator is accelerating upward. I called it B here, but usually I would call that the normal force. The normal force is more than the weight. That's what makes it accelerate, okay? But these are not an action-reaction pair. This is the gravity pulling on the box. This is the floor pushing on the box. Action and reaction do not act on the same body, okay? If you go back to the way it says it here, you've got one force acting on object B and the other one acting on object A. It's all about how two things push on each other. One force on the one, the other force on the other object. Action and reaction do not act on the same body. So, yes, the weight is less than the normal force. That's why it accelerates, because you have a net upward force. And that actually has absolutely nothing to do with this. Oh, now the focus is doing its little throbby thing. And we'll go back to doing it the other way. Just takes a second. The weight and the normal force are not equal. The normal force is greater, and that has absolutely nothing to do with this question here. This is about how the force on the box compares to the force on the floor. They are an action-reaction pair. Force B and the weight of the box are not, okay? Another example. As I sit here, the Earth's gravitational field pulls down on me with a force of about 180 pounds. The question is, what is the reaction to that? People get this wrong quite frequently. So in case I was to ever ask you this again, pay attention, and maybe you won't be one of them. The reaction to my weight is not the normal force. Yes, as I sit here, the normal force equals my weight. That's because of Newton's first law, not the third. I am an object at rest remaining at rest, and so the forces on me have to balance out. The force down has to equal the force up. If I was riding in an elevator, my weight would not equal the normal force. That was the previous question that I just got done talking about. So the reaction to a force on me is not another force on me. Rather, let's go back up here to where it says the third law. My weight comes from the Earth. That's the Earth pulling on me. So if the Earth exerts a force on me, then I exert an equal and opposite force on the Earth. The Earth and I pull on each other. Gravity behaves in some ways as if I was connected to it by some kind of invisible rubber band, okay? If I jump up in the air, this rubber band tied around my ankle pulls down on me with the one end and pulls up on the Earth with the other end. We pull on each other. You see, I have a gravitational field too. Gravity is a universal property of matter. Every object in the universe attracts every other object. I mean, if some guy wants to use it as a pickup line, you know, he goes up to some girl, hey, I'm attracted to you, and I know you're attracted to me. It's true. She should probably still punch him, but it's true, okay? The force is extremely small because, you know, there's not a lot of mass for each object. But even though my gravitational field is quite weak, there's an awful lot of the Earth to attract, and it evens out. I weigh 180 pounds in the Earth's gravitational field, and the Earth weighs 180 pounds in my gravitational field. If you wanted to measure that for yourself, just go home, get the bathroom scale. You'll have to think of some way of reading it with it turned upside down. But if you could do that so that the Earth is sitting on the side of the scale that you usually stand on to weigh yourself, and you stand on the back of it where the Earth usually is, you'll find it says the same thing as when it's right side up. So anyhow, here's the action and the reaction. The Earth and I pull on each other gravitationally. Now, the Earth's mass is more than 10 to the 24th kilograms. 180-pound force on something that massive has no measurable effect. But if you want to talk about the Earth and the moon, rather than the Earth and a person, it becomes quite measurable that they're pulling on each other. Both of them are freely falling objects in each other's gravitational fields, as I think I already talked about a week or two ago. So anyhow, things that would give you clues to keep in mind if asked a question like either one of these. Action does not act on the same body as the reaction. Furthermore, action and reaction are always going to be the same kind of force. The reaction to a gravitational force is another gravitational force. The Earth's gravitational force on me, my gravitational force on the Earth. The reaction to a contact force is another contact force, okay? The normal force pushing up on the box, the normal force pushing down on the floor of the elevator. So that's Newton's third law. Now, from there we move on to conservation of momentum, which might seem like I am leaping to an entirely different topic. Why did I put these together in the same unit? Well, it's because it's not an entirely different topic. The third law and conservation of momentum are really, as we'll see here pretty soon, they're really just two different ways of looking at the same thing. So, definition, first of all. Momentum is mass times velocity. It's a little bit like kinetic energy in that it's determined by an object's mass and its velocity, but it's not quite the same thing. Kinetic energy is 1/2 mv squared, no 1/2. You don't square the velocity, so the momentum is different kind of that way, but probably the biggest difference is notice the little arrows over the P. I don't know why they use P for momentum. I mean, I know why they don't use M for momentum, because M was already taken for the mass, but, well, somebody just drew a letter out of a hat, I guess, and it's become pretty much the standard notation. But notice the little arrow over the P and over the V. Momentum is a vector. whereas kinetic energy or any other kind of energy is a scalar, and that makes a lot of difference. So that's the definition. Consider two objects that are pushing or pulling on each other. This could be two balls colliding on a pool table, for example. During the collision, ball one pushes on ball two, and simultaneously ball two pushes back on ball one. Or it could be two, the Earth and the Moon pulling on each other gravitationally, or anything else. But the third law says that their forces are equal and opposite. Okay, you've got the two balls pushing against each other. One pushes on two, two pushes back on one. This is an action-reaction pair. So the forces are required to be the same by the third law. Because, well, I won't go through the whole chain of reasoning here, but to make a long story short, but it's not that long of a story, but to make a medium length story short. Because the two objects feel equal and opposite forces for equal amounts of time, the changes in their momentum come out equal. In other words, the momentum lost by one equals the momentum gained by the other. And so that means the total between the two of them stayed constant. Or it doesn't have to be two objects. You could have a whole swarm of asteroids pulling on each other gravitationally, and it's still true that it's a more elaborate version of the same argument, but it's still true that the total momentum in the entire collection of objects stays the same in both magnitude and direction, because momentum is a vector. It's conserved as a vector. So here's where I run through an example to kind of illustrate that. And then you'll do this next example. And then, of course, there's more fun on the next page. So 7A. I usually like to draw before and after pictures, or sometimes one comes with the question, so you don't have to draw one, but let's see. So the bullet is going 190 meters per second. Oh, I probably should have written down the answer here. I guess it wasn't on the other thing. A equals B because of the third law. Anyhow, before and after. So here we have a bullet, mass 20 grams, and it's going 190. Meters per second. And dead ahead, there's a 4 kilograms even, 4.00 at rest. So it's just sitting there minding its own business, and along comes this bullet. Well, actually, for a bullet, 190 meters per second is pretty slow. And so it doesn't make it out the other side of the block. Rather, afterward, we've got something kind of like that. So there's the bullet inside the block of wood, and the combined bullet block system is moving with some speed that I'll call V. And finding V is what I'm supposed to do. V being the speed of both the block and the bullet, because the bullet is inside the block. Conservation of momentum says that if you add up the momentum of both the bullet and the block in the before picture, it's got to be the same total that you get in the after picture. Momentum is mass times velocity, so momentum of the bullet, 0.02 of a kilogram, times 190 meters per second, plus momentum of the block, well, it's just sitting still. I mean, 4 kilograms times 0 if I wanted to write it down, but that's 0. Afterward, the bullet is still 0.02 of a kilogram, and it's going with a speed that I'm calling v. And the block is still 4 kilograms, and it's moving at the same speed. In some other question, like, two balls colliding on a pool table where they bounce off each other, then you'd have two different velocities, v1 and v2 in the end. But in this case, v1 equals v2 because they're stuck together. So over here, 190 times 0.02 is 3.8. Over here, you can factor out the v with the distributive property, and you get 4.02 times. Or you can just, maybe the easier way to look at it, I was just kind of trying to be general in the way I set it up, but in this particular example, the bullet and the block have effectively merged and become a single object whose mass is 4.02 kilograms. Anyhow, finishing the math. 0.945. So, for you, I don't know why this does that. Stop it, I say. All right, we'll do the screen share. It's a little more cumbersome to go back and forth, but where is that? Okay, that should be pretty legible. So this one that I'm going to have you do is kind of like the one I just did, only backwards. Here, the one I just did, you've got two things that come together. And here you've got what starts out one thing and it pops apart. I don't know if you can see anything on the little window over on the side there, but if this was before and if this was after, then this would be like the bullet inside the gun, and then of course the bullet would be going the other way afterward. But anyhow, you work on that, and this is where you should pause it. Now this, as soon as I get back to my clipboard, is where you should unpause it. Okay. Before and after. Total momentum in the before picture will equal total momentum in the after picture. That's where our equation comes from. That slightly resembles a gun. And immediately after being fired, that bullet is going 300 meters per second. It says 5 grams, which is also known as 0.005 of a kilogram. The gun is 5 kilograms, and it's going the other way. Or at least if you're foolish enough not to have it pressed tightly against your shoulder, it's going the other way at a speed v. And maybe I won't bother drawing a picture over here. Let's just say both, meaning both the gun and the bullet, are at rest. So just imagine another picture of the gun that looks kind of like this one, with the bullet inside of it, and the speed of both of them is 0. So total momentum in this picture equals total momentum in that picture. Nothing is moving before. So the total momentum after you fire the gun has to be 0. What happens is, since you give the bullet some momentum in the positive direction, the gun has to pick up some negative momentum in order for the total to still be 0. Or you can think of it as action and reaction. The bullet gets thrown. It's like when I was talking about standing on the skateboard and throwing a ball. Same principle. You throw the ball, it gets some momentum in the one direction. You have to roll back in the other direction, getting an equal and opposite amount of momentum. So anyhow, mass times velocity here. 5 kilograms times the speed v, plus, now maybe I should choose my words more carefully, the velocity v. Mass 0.005 and a positive 300 meters per second. So mass times velocity, and over here mass times velocity. Well, this is equal to 1.5 when you multiply it. So you're going to have, if I subtract this from both sides, I'm going to have negative 5v equals 1.5. And so dividing through by the negative 5, you get negative 0.30 meters per second. Now, actually, if you want to nitpick about the way the question is phrased, it doesn't say find the gun's final velocity. It says find the speed. Well, speed is a scalar, okay? Speed just means how fast is it going. I don't care about the direction. So the speed would actually just be the 0.3. And at the very bottom of the page, it says here that the same effect is responsible for rocket propulsion. I don't know why it focuses on the clipboard without all that throbbing, but doesn't want to do it on the, I don't know. Anyhow, rocket propulsion. A gun throws a big chunk of mass all at once and gets a kick all at once. With a rocket, you have a continuous flow of tiny little microscopic bullets, the individual molecules of fuel being expelled at very high speed out of the back of the rocket. As you continuously expel mass in the one direction, you will get a continuous recoil in the other direction. And that's how a rocket is able to develop thrust in a vacuum where there's nothing around it to grab onto. Airplanes basically swim in the atmosphere. If you don't have any air, an airplane couldn't get off the ground. You can, and you can't fly them up high where the air gets too thin. Depending on what kind of airplane, I don't think you're going to get it up more than maybe 6 miles, if that. Balloons will actually go significantly higher than airplanes will. But of course, they have their limits also. Rocket you can take to Mars, and this is how it's able to develop thrust in empty space. So we turn the page. And the first thing it says is that in the example we just went through, notice that E, where E here doesn't include all types of energy. It does not include heat or chemical energy or any of those other non-mechanical forms. E here means kinetic plus potential. So with everything sitting still, there is no kinetic energy. Of course, it's level, the gun and the bullet are moving horizontally. So there's no change in potential energy anywhere. Nothing's going uphill or downhill. The kinetic plus potential would just be the kinetic energy by potential energy just stays zero. And there's no kinetic energy here because nothing's moving. Over here, that's moving, so it's got some kinetic energy. That's also moving, so it's got a little bit more kinetic energy. You add it up. Of course, kinetic energy is a scalar. It's never negative, okay? 1/2 mv squared, if the velocity is negative, you lose the minus sign when you square it. Kinetic energy is always positive. It has no direction. And no other reason it can be negative either. And so no kinetic energy, but here there is kinetic energy. Kinetic energy is not conserved because, where did the energy come from? Well, it was the chemical energy that was stored in the gunpowder before you fired it that got transformed into kinetic energy. So a common mistake is for people trying to use conservation of energy when they shouldn't. Now, momentum methods frequently get used to analyze collisions. Collisions are not, conservation of momentum is true in general. You could use it, like I said earlier, talking about asteroids or planets pulling on each other gravitationally. But momentum, you've got different alternatives for how you can approach a problem. And the momentum approach seems to be particularly well suited to analyzing collisions. And so that is at least among the ways it gets applied. So I give people a collision on a quiz or an exam, and there's always somebody, usually more than one, who wants to use total 1/2 mv squared before equals total 1/2 mv squared afterward, and they get the wrong answer that way. Because, like I was just saying, energy can be converted into or out of other forms. What it comes down to is whether the objects are permanently deformed by the collision. If you have two things like balls on a pool table, nice hard objects that collide at a pretty low speed so that they aren't damaged in any way, basically those two balls, when they hit, kind of squish together and then they pop back, and it's almost like a collision between a couple of springs. And in a case like that, kinetic energy will be conserved, or fairly close to it at least. That's called a perfectly elastic collision. The opposite extreme is a perfectly inelastic collision, which is one like this example that I did earlier, where the bullet ends up inside the block of wood. A collision where they stick together is about as far, well, I'm not going to bother to write it out, but as an optional exercise for the student, every time one of my professors said that, I always kind of snickered, but as an optional exercise for the student, I invite you to calculate how much kinetic energy this bullet has here, and then how much kinetic energy there is over here after the collision, and you'll find that there's far, far less kinetic energy here than there was there. Where did it go? It got changed into heat. As the bullet pushed through the block, there's a lot of friction. And the bullet ends up hotter than it was before, so does some of the surrounding wood, and only a small fraction of the original kinetic energy is still in that form, kinetic energy, over here. Quite a bit more of it gets changed into heat. So anyhow, unless the question specifically tells you you're dealing with a perfectly elastic collision, or some other words to that effect, do not use conservation of 1/2 mv squared, because that's a good way to get the wrong answer. Energy can be converted from or to other kinds of energy. mv is the only kind of momentum there is. Momentum is conserved in any collision, whether it's elastic or inelastic or anywhere in between. Momentum is always conserved. So anytime you see a collision, your conditioned response, like Pavlov and ringing the bell at the dog, if you don't know what I'm talking about, take a psychology class. But anytime you see a collision, your conditioned response should be to think of conservation of momentum. Do not try to use conservation of kinetic energy unless the question tells you it's okay, perhaps by using the code words perfectly elastic. The other thing to keep in mind is to remember that momentum is a vector. These ones that I already went through, those were one-dimensional problems. So, everything stayed on the x-axis, so you didn't have to get involved with components or anything like that. But if it's a two-dimensional collision like these next problems, then you need a full-blown vector treatment with sines and cosines and components and all of that. So, as usual, I'm going to, now, I would invite you, if you think you've got it, to try and do both of these on your own. The more you can do yourself, the better off you are. But what I had in mind when I wrote out these notes is that I'd run through this one, and then you could use this for sort of a pattern to imitate as you work through this one. Although there are a few differences, just enough to keep you on your toes. So this could be two balls colliding on a pool table, except, well, no, they could be, that's exactly what they probably are. Both balls are the same mass, just like billiard balls would be. And so given exactly what's going on before the collision, you're supposed to predict what the final, and you're given the directions they move after the collision. You're supposed to predict what the speeds would be, V1 and V2. So let's see, 7B I called this. So before. Now, it's just like, well, it's not just like, but it's very similar to other situations we encountered where you needed to deal with vectors. Think in terms of components, okay? Section 2, I think it was, where we did projectiles. You need to write equations for the x, you need to write an equation for the x components and another equation for the y components. And then a couple of weeks later, I think it was section 5, you had a box sliding down a ramp. And there again, you had to write an equation for the, this time it would be x and y components of the forces. Write an equation for the x components, sum of the forces in the x direction equals ma, and write an equation for the y components. Here again, write an equation for the x components, write another equation for the y components. 99 times out of 100, that's the way to deal with vectors. This time it'll be momentum in the x direction and momentum in the y direction. So in order to do that, we have to have the components of everything. So in my before picture, I've got a mass m, and it's moving. I'm going to make that nice and big so I've got lots of space to label some things. And there's the other ball right in front of it where it's going to get hit. Mass times 5 meters per second. Okay, momentum equals mass times velocity. And the direction of the momentum vector, well, it shows back here in the picture that that arrow makes a 43-degree angle with the x-axis. Kind of like this. So we need to get the components. That's the x component, that's the y component. We've got 5 times m for the hypotenuse. Momentum equals mass times velocity. This is the momentum vector that I'm finding the components of. So, well, I didn't leave myself a lot of space to write over here. If I was in the lab, I couldn't turn the blackboard sideways like this, but I've got the hypotenuse, 5m, times okay. Y component is the opposite side of the triangle, hypotenuse times sine. Adjacent side is hypotenuse times cosine. And this thing is just sitting still, v equals 0. After the collision, well, we've got one mass headed in that direction, 77 degrees above the x-axis. The direction of the momentum vector is the same as the direction of the velocity vector, because mass is a scalar, okay? You multiply a vector times a scalar, and you get another vector that points in this. All a scalar does, multiplying by a scalar, just makes the arrow get shorter or longer. It doesn't affect its direction. So momentum has the same direction that the velocity vector does. Mass times V1. And so the components of that well, it's the usual thing. Hypotenuse times the cosine over here. Hypotenuse times the sine for the opposite side. And then The other ball, after the collision, is headed right down the x-axis. So I'll draw that too. So a little while after the collision, it's maybe a little below and to the right from the other one. And it's just going that way with a speed that I'll call v2. So the x component of that one is just m times v2, and its y component is 0, because this arrow doesn't point up or down at all. It has itself for an x component and 0 for a y component. Okay. Total momentum, well, it's two equations now, okay? Just like F equals ma can be divided up into some of the forces in the x direction equals m times ax, and some of the forces in the y direction equals m times ay. Same sort of thing with conservation of momentum. Conservation of momentum in the x direction gives us one equation. Conservation of momentum in the y direction gives us another equation. And between those two equations, we can calculate the two things we're trying to find, v1 and v2. Okay, so x momentum. Every place there's a horizontal arrow in this picture, that becomes a term to the left of the, the way this always works is to the left of the equal sign is before, and to the right of the equal sign is after. So to the left of the equal sign, taking things out of the before picture, we have 5m times the cosine of 43 degrees. And it's not really worth writing down, but the momentum of the other ball is 0 because it's not moving. Other side of the equal sign is after. Every place there's a horizontal arrow in this picture, that's one of the terms to the right of the equals. Well, we've got m times v1 times the sine 77 degrees plus, there's another horizontal arrow, mv2. Now, the question didn't tell us the mass. Good thing we don't need to know the mass, because notice, if you divide through by the mass, m over m equals 1, 0 over m is 0, m over m is 1, m over m is 1. The mass drops out. 5 times the cosine of 43 degrees equals 3.66. The sine of 77 is, rounding it off a little bit, 0.225 times V1. And then we've got the V2. So even after canceling out the mass, we have two variables in this equation, which means, you know, one equation, two variables, you can't solve that. So we'll just have to put that aside. Might be useful, well, turns out it is useful later. But let's try the y components and see if we have better luck. And if I'd had a little more foresight, I would have written down this equation first, because it turns out that this equation will only have one variable in it, and that will be solvable. But it doesn't matter if you don't notice that. You know, you'll get to this sooner or later. Sometimes you just have to start bumbling around and flinging around equations until you stumble on the right one. So now, It's every place there's a vertical arrow that becomes a term that goes in here. So that's in the y direction. 5m times the sine of 43 degrees. And here again, if I wasn't trying to be step by step and methodical, I wouldn't even bother writing this down because it's just a 0. But that's for the other ball. Total momentum is the mass of the one ball plus the mass of the other ball, or times velocity. mv for the one ball plus mv for the other ball in the y direction, y components. Over here, on the after side of the equal sign, well, there's a vertical arrow, mv1 times the cosine of 77 degrees. There's no vertical arrow here. The y component is 0. And so there's that. Once again, just like in the x equation, the mass drops out. If you divide through by m, it's gone. So you've got 5 sine of 43 degrees equals v1 cosine 77 degrees. To solve it, see, this only has one variable in it, so now we're going to get somewhere. Divide both sides by the cosine of 77. That cancels out there. So 5 times the sine of 43 divided by the cosine of 77, and that comes out 3.50 meters per second. Here's one of our two answers. Okay, well now this equation becomes useful because I can stick that 3.5 in for V1, and once I've done that, then I'll get an answer for V2. So 3.66 equals 0.255 times 3.5. Okay, we're almost there. This is 0.79. You subtract it from both sides, and you get 2.87. Almost lost half a point on my own quiz here. Got to label the unit. Okay, so that one, here, let's do the screen share thing so you've got a nice clear look at the question. And we're on the next page now. Okay, so I just did this one down here where it says 7.2. That's what I want you to work on next. One important difference to notice, the one I just went through, the masses were the same. That was the reason that, remember, they canceled out, divide through by them and they're gone. Here you've got two objects with different masses. The mass will not drop out the way it did in the previous question, but that's okay because this time you've got numbers you can fill in for the masses. So pause it here. And now unpause it. And as soon as I get things back on my clipboard, let's do, I guess, solutions on the next page over here. Let's do number 2. Okay, so 70 kilograms here, which means the momentum of that astronaut is 70 times 1.2 meters per second. Incidentally, there is no special name, like for energy, a Newton times a meter is a joule. It's given a name of its own. There is no special name for the SI unit of momentum. It's just simply kilograms times meters per second is what this is measured in. Or a little more compact than that, kilograms times meters per second is equivalent to newtons times seconds, if you wanted to label it that way. But anyhow, the hypotenuse is 84 units long, and we have to get the components. Question tells us this is a 69-degree angle, so x component of the momentum, 84 cosine of 69, 30.1. The y component, 84 sine of 69 is 78.4. And there's probably one person out there who's saying, well, that's exactly what I punched up, but I didn't get those numbers. Yeah, you're the person whose calculator is in radian mode. Put it in degrees and try that again. Over here, where I didn't leave any space for it, there's the 60-kilogram astronaut at rest. X component equals 0, Y component equals 0. So that's the situation before the collision. After the collision, the 70-kilogram astronaut is going right straight up the y-axis. As I said, right straight up. I drew a really crooked line, but that's mass times velocity. 70 times the speed of that one is v1. The question called the 70 kilograms astronaut's velocity v1. So it's right straight up the x-axis, or right straight up the y-axis. The x component would be 0 for that one. Maybe that's worth writing down. Px equals 0, Py equals 70 v1. And then we had the 60-kilogram astronaut. Mass times velocity, 60 times v2 is that one's momentum. 36 degrees above. Well, I'm not going to say above the horizontal, because then that gets into the question of which way is up in space. But whatever it is we're calling the x-axis, 36 degrees relative to that. So hypotenuse times cosine for the adjacent side, 60 v2 cosine, 36 degrees. And we might as well multiply the numbers together. Might as well do that sooner rather than later. 60 times the cosine is 48.5, and we have that times v2. And then here we've got 60 V2 times the sine of 36 degrees, and 60 times the sine of 36 is 35.3. And that's times V2. Okay, so we've got all our components all figured out. Time to start flinging some equations around. Conservation of momentum in the x direction. And this time it'll be x where there turns out to be just one variable in the equation, because this thing has no x component. The only unknown in the x direction will be V2. To the left of the equals, before, we've got a horizontal arrow with a 30.1 written next to it. And the momentum for the other astronaut is none at all. Over here, no x momentum for this person. Horizontal arrow with 48.5. Written next to it. So we've got 30.1 equals 48.5 V2 without all the zeros. And then to solve it for V2, divide both sides by the 48.5. So you just got 1 times V2. And when you divide 30 by 48.5, you get 0.620 meters per second. In the y direction, before the collision, the y momentum of the one astronaut is 78.4. The y momentum of the other one is 0. I'm not going to write down the 0 again. I think by this point you get the idea that it's supposed to be the total of both astronauts before and the total of both astronauts afterward. And the reason I'm not writing down anything for this one is that it doesn't have any momentum. Both of these have vertical arrows. So we've got 70 V1, and we've got 35.3 V2, but rather than writing down V2, I now know that V2 is equal to 0.62, so why don't I put a 0.62 in there? And then, well, that times that is about 21.9. So you subtract 21.9 from both sides, and you'll have 56.5. Okay. 78.4 minus 21.9 is 56.5. Divide this out for V1. 0.808. And as I'm sure I've said before, if you weren't able to get that yourself without watching me do it, and I know there's several of you out there, My recommendation is that rather than going recklessly onward into the next example, you pause again here and see if you can do it yourself now. Because if you still can't do it yourself, it's not going to get any better by waiting. But assuming that you are successful with number 2, here's number 3. You've got a 1,000 kilogram car going in the X direction at that speed, and another car going up. They meet at an intersection. You know, they're one's going east and one's going north, and somebody was not looking for stop signs. So we're going to say that this is probably not completely realistic. The cars would typically bounce off each other at least a little bit, but one way or another, you know, the bumpers get locked, you know, hooked through each other, or something happens that they end up stuck together. That's what a perfectly inelastic, that was further back up the page. A perfectly inelastic collision is one where they stick together. So find the magnitude and direction of the velocity of the combined mass of metal just after the collision, immediately after the collision, before friction, you know, rubbing against the ground has a chance to slow it down. So pause again. And now I'm going to do it. X-axis, Y-axis. So here you've got a car with a mass of 1,000 kilograms. And it says it's going in the X direction at 25 meters per second. This is like looking down on the intersection from above. You're in the traffic helicopter watching all of this. A somewhat heavier vehicle going 20 meters per second. After the collision, well, you have this blob of metal that was originally 2 cars, kind of going in that direction with some velocity v. And just like the question where the bullet got shot into the block of wood, they have effectively merged into a single object whose mass is going to be the total. You've got 2,500 kilograms here for the mass. The momentum will be that times the velocity, but we're more interested in components because that's what usually makes vectors better to work with. So the hypotenuse is v, its y component will be vy, and its x component will be vx. Finding v and also theta, I should probably label that on here. Finding the speed and direction is what the question asks for. Magnitude and direction of the velocity. The way I'm going to do that is by using conservation of x momentum, I can get Vx. By using conservation of y momentum, I can get Vy. And once I know Vx and Vy, I can get the hypotenuse from the Pythagorean theorem, and I can get theta by doing a little trigonometry. And if you're sitting there saying, oh, why didn't I think of that? Well, if you see how to finish it off from here, pause it and finish it off yourself. I mean, I already know how to do this. I don't need to practice. Anyhow, I'm going to assume now that everybody is back. Conservation of x momentum. Conservation of mv in the x direction. I've got mass times velocity for the one car. This other one that's going right straight up the y-axis has no momentum in the x direction. Over on the other side of the equal sign, the x component would be 2,500 times Vx. So every place there's a horizontal arrow before, that goes to the left of the equals. Every place there's a horizontal arrow after, that goes to the right of the equals. The hypotenuse, the momentum would be 2,500 times V. The x component is 2,500 times Vx. Anyhow, if you divide both sides by 2,500, I can just barely squeeze in over there, that this x component is 10 meters per second. Now the y components. Well, this one has no momentum in the y direction. All of the y momentum is originally in this car. 1,500 times 20. Afterward, we've got the 2,500, the total mass, times Vy. Just like before, divide both sides by 2,500 to solve it for Vy. And that comes out 12. So what we have now is you got 10 on this. I'm just redrawing this triangle here, kind of without all the clutter around it. To get the magnitude of the velocity, that's the Pythagorean theorem. Comes out 15.6 meters per second. To get the angle, well, now that we know the hypotenuse, you could use any trig function, but I'm sort of in the habit of using the tangent. Tangent is opposite over adjacent. So the inverse tangent of that would be the angle theta, and that comes out and that's what I had to say to you about momentum, but there's a little more to section 7. Section 8 and beyond deals with rotational motion, and we get some of the introductory definitions and things out of the way. Oh, it's doing that again. I don't understand why. Okay. There, that probably looks a little better. So anyhow, some of the introductory comments about rotational motion. Consider, well, that reminds me, I wanted to put some air in my bicycle tires today. This could be a wheel on a bicycle. Got it flipped upside down. I should put some lube on the chain while I'm at it. I haven't done that for a couple of months. So you got your bicycle upside down, and you're doing all that stuff I was just talking about. You give one of the wheels a little bit of a spin and it's going around, and that could be what we're looking at here. Or, you know, this could be a gear spinning inside of a transmission, or the blades spinning around on a fan, or could be the air circulation inside of a tornado. There's all sorts of situations where rotational motion comes up. This reference point, that could be the stem where you put the air into the bicycle tire. And when you first look at the bicycle tire, that reference point is there. A short time later, just, you know, like half or 3/4 of a second, now that valve stem is up here instead. And if you draw a line from its initial position to the center of the wheel and a line from its final position to the center of the wheel, that makes an angle theta. This distance that I've labeled S, that's how far that point has moved. If this was section 1, we'd call that delta x, but I think I've gone through this little speech before. Delta x kind of implies you're moving along an x-axis, and this is following a circular arc instead, so that's the reason for picking a different letter, but it's S is how many meters did it go. Theta, well, that could be measured in degrees, or, you know, if the wheels turned just a little bit, you would be inclined to say something like, the wheel turned 30 degrees. On the other hand, if you watched it for a long time, you're more likely to call that 100 revolutions than to call it 36,000 degrees. So revolutions for a large amount of movement, if it spins a long time. Degrees is typical for a small amount of movement if you're watching it for a very brief time. And I'll get back to that on the next page, but some other stuff that will be on the next page. Rotational motion is described basically by recycling the same concepts we used in section 1 to describe motion from place to place. The first step was a variable to tell you how far. Okay, you've got a car going down the road. Delta x tells you how far did it move down the road between when you first looked at it and when you stopped looking at it. Well, with rotational motion, how far is described with an angle rather than with a distance. Next step, you might want to talk about how fast the car is going down the road. That was the velocity, delta x over delta t. Well, how fast something is spinning around is described with an angular velocity, which would be delta theta over delta t. And, you know, all of this is coming up further down the page here, but I just thought it would be good to have a handy little list where it's all collected in one place, what these different letters mean. Greek letter theta, the Greek letter omega for how fast. Everyone wants to call that a W. Well, I guess nobody's going to die if you call it W, but actually it's a Greek O. The Greeks don't really have a W in their alphabet. I'm not quite sure what the difference is between omega and omicron. I should look that up sometime. Anyhow, the rate at which the velocity changed when we talked about motion along a straight line, the rate that v changes was the acceleration a. A was delta v over delta t. Delta omega over delta t is the angular acceleration represented here by the Greek letter alpha, which almost looks like an A. It is a Greek A. So anyhow, we'll fill out the details on the next page. I just wanted to have a compact little list that you could refer to, because people get these symbols mixed up with each other and forget what they mean. So to finish talking about units to measure theta in, I said, you know, you could use degrees, you could use revolutions, or you can measure it in radians. Now, degrees and revolutions are kind of handy for taking measurements. Any protractor I've seen is measured in degrees. If the wheel is going to go around 100 times, you know, you just sit there and you count that it went around 100 times, and it gives you in radians, or that gives you revolutions. Radians is often the nicest thing to have when you're doing certain types of calculations. But before we get to that, what exactly is a radian? Well, back up here to the picture. Let's say you never heard of degrees. Maybe that was the week in 4th grade when you were out sick, or whatever grade they cover that in. So, I mean, you know, a degree is really an arbitrary thing anyhow. Why take a circle and divide it into 360 units? Wouldn't it be nice to have some sort of a metric degree where you divide it into 100 units instead of 360? Why 360? Because the Babylonians were into multiples of 60. That's why. It's something people started doing 3,000 years ago. And since then, it's always been, well, we just do it that way because that's how it's always been done. But it's really just an arbitrary number, 360. So let's say somehow you got missed and didn't know about that. And you're trying to think of some way to describe to somebody how far your bicycle wheel is turned. Well, this point on the edge of the wheel here, maybe it moved 10 inches, okay? That would be this distance I labeled S. And you're about to say my wheel turned 10 inches, when it crosses your mind that that's just the outside edge of the wheel that's moved 10 inches. A point in here that's halfway to the center, it only moved 5 inches. Or a point here that's a third of the way out, it only moved 3 1/3 inches. So, you know, especially if the wheel was some kind of solid object instead of just being a bunch of spokes in the middle, you know, like if it was the grinding wheel on a bench grinder, can't say it moved 10 inches. That's just the outside edge. But wait a minute. Half the radius, half the distance, a third of the radius, a third of the distance. The ratio is always the same, whether you're out here on the edge or anywhere else. The arc length divided by the radius is something that is the same for every point on the wheel. Theta equals S over R. So that's kind of a natural way of describing angles that doesn't involve just pulling a number out of a hat, 360 or whatever. And that's what a radian is, okay? Theta in radians is the ratio of this arc length divided by the radius. Theta equals S over R. Or the way it's written on the formula sheet is S equals R theta. No, easier to type that way instead of fooling around with a fraction, but same thing. Notice that an angle in radians is just a dimensionless number. A radian is not actually a unit in the same sense that a kilogram or a joule is a unit. Well, this would be a pretty small bicycle wheel, but if you had a grinding wheel with a radius of 5 centimeters and a point on the outside edge of it moved a distance of 10 centimeters, how far did that wheel turn? Well, theta equals S over R. 10 centimeters over 5 centimeters. 10 over 5 is 2, but the point here is the units rather than the numbers. Notice centimeters over centimeters cancels out. It's just a 2 with no units on it. It's a dimensionless ratio. And I think I mentioned this before because a friction coefficient is another example of a dimensionless number. Mu equals F over N. You've got newtons divided by newtons. There again, it's a number without a unit. A dimensionless quantity is one that takes on the same value in any system of units. If you decided to measure in inches, well, 5 centimeters is just about 2 inches. 10 centimeters is just about 4 inches. 4 divided by 10 still comes out 2. So whether you're measuring in metric or whether you're measuring in inches, theta comes out the same number of radians. It's a dimensionless quantity, something that's the same in any system of measurement. But I will usually write it as theta or as 2 radians rather than just writing theta equals 2. Because if I wrote down theta equals 2, everybody would think I meant 2 degrees. So need to clarify that, but you need to understand that it's actually just a dimensionless number. Otherwise, you'll get kind of baffled when it appears and disappears as if by magic. Well, there's some examples of that coming up. Meanwhile, definition of angular velocity. Just as average velocity is delta x over delta t, average angular velocity is the rate that the angle changes with time. As I already mentioned, the thing that everybody wants to call a W is actually a Greek omega, lowercase omega, actually. The Greek alphabet has large and small letters just like we do. So here's a piece of thoroughly obsolete technology, except actually it's having kind of a renaissance. There are people who are really seriously into vinyl these days. But anyhow, when I was a kid, there were no MP3 files. In fact, they didn't even have 8-track tapes yet, let alone compact discs. We had records. Or you turned on the radio. Well, actually, we did have tape players, but it was open reel tape. It wasn't in cassettes. But anyhow, if you have a record player turntable and you put on your copy of Dark Side of the Moon and watch the record go around, counting the revolutions, you'll find that in exactly 3 minutes, that record will spin 100 times. It'll make 100 revolutions. Find the angular velocity in both revolutions per minute and also radians per second. So pause it here. And now unpause, and I'll get the thing I write on back again. So that was number 4. Hold on. Oh, that's what I'm looking for. Okay. Angular velocity, omega. Change in the angle over the change in time. Now, technically, it said omega average in the note packet, but a record spins at a constant rate, okay? The angular velocity remains exactly constant unless you've got an old worn out record player where the belt is slipping and then the music sounds really terrible. So because this never changes, there's no need to distinguish between the average and the value at any instant. It's 33 1/3 RPMs all the time, And so if you average all the different times, you get 33 1/3. But I'm getting ahead of myself. 100 revolutions divided by 3 minutes revolutions per minute is often abbreviated RPM. If you have a car with a tachometer on the dashboard, personally, I've never understood why cars with automatic transmissions need a tachometer, but I have seen them. I have owned them. The tachometer reads in RPMs, and it's telling you the angular velocity of the crankshaft in the engine. How fast is the crankshaft spinning around? Well, the question asks us to convert that into radians per second also, and that works just like all of the other unit conversions we've seen before. You know, whether you're converting horsepower into watts or miles per hour into feet per second or whatever it is, you multiply by a fraction where the top equals the bottom, kind of like this. 33 1/3. Better to write revolutions divided by minutes. If you just abbreviate it with RPMs, that is going to be very unhelpful in what you need to do next. So multiply by a fraction where the top equals the bottom, and you want you need to set that up so that the unwanted units cancel out. So to get radians per second, we need to get rid of the minutes. Since minutes is on the bottom, you need to have minutes on top in this fraction so that it'll cancel like that. And seconds is the unit that you want to have instead. Once you've figured out which one belongs where like that, fill in the numbers. And this is one that you will not be able to look up on your formula sheet, because I really hope you already know that 1 minute equals 60 seconds. As for revolutions, we need to turn that into radians. Since revolutions is on top, we want to have revolutions on the bottom over here. So that will cancel. And radians is what we want to have instead. Well, this time the conversion factor is one that you can look up on that last page of your formula sheet, in case you don't remember it. But 1 revolution is equal to 2 pi radians. So that tells you that you should be multiplying by 2 pi and that you should be dividing by 60. Once you get that figured out, get out the calculator, punch it through, and that comes out 3.49 radians per second. The number of radians per second equivalent to 33 1/3 RPMs. Continuing. Okay, we did that. Angular acceleration. Just as alpha, or just as A equals delta V over delta T, now that we're talking about rotational motion, it's angular acceleration represented by alpha, and that's delta omega over delta T. So let's say you've got a fan and you decide to turn it off. Well, it doesn't instantaneously stop. There's a transition period when it's coasting slower and slower. And let's say that in this case, it takes 10 seconds for the fan to come to rest after you switch off the power. What does that make its angular acceleration? Well, I've got it all written out here. Delta omega over delta t. Delta omega means omega final minus omega initial. The final is 0 because it stops. The initial was the 4 given in the question. Time for the change is the 10 seconds that it says over here. So 4 over 10, you've got 0.4. It comes out negative because the fan is slowing down, just like the translational velocity. If you've got a car going down the road and it's coming to a stop, acceleration will be negative because the velocity is decreasing. Here, the angular velocity is decreasing. It's losing speed. That gives you negative acceleration. Revolutions per second squared, just like linear acceleration would be meters per second squared. Back in section 1, after I went through the basic definitions, what does velocity and acceleration mean? I said, let's consider a special case. What if the acceleration is constant? Well, for that special case, and that special case only, there was a group of 5 equations, and you use them to solve, questions about freely falling objects, and there was one with an airplane gaining speed on the runway and that sort of thing. Well, now for rotational motion, now that we've got the definitions out of the way, let's consider a special case. What if the angular acceleration happens to be constant? Once again, there's a little group of 5 equations. This time having my hand there seems to be messing it up. Okay, back to this. 5 equations to describe uniformly accelerated rotational motion. And actually, if you look at it and think about them for a little while, they should have sort of a familiar feel to them. They're really the same equations, okay? It's like one of them back in section 1 was delta x equals v initial t plus 1/2 at squared, or another one was v final squared equals v initial squared plus 2a delta x. The rotational quantities are defined the same way that their translational counterparts are. If you take what amount to the same definitions and manipulate them the same way, you can end up proving the same 5 equations. They're just dressed up in a different suit of clothes is all. Instead of regular Roman letters, you've got Greek letters because now we're talking about rotation. You would use these equations the same way. In fact, the list of what you're given and what you're trying to find is even more important now because it was probably not that hard to see that V stood for velocity and A stood for acceleration and that kind of thing back in section 1. But now you've got all these Greek letters, these cryptic symbols. So you need to think carefully about what each one means. And, don't be afraid to use the formula sheet for a little bit of guidance. Like, I don't have well, I could go to the formula sheet, I suppose. Here, wait a second. So if you're trying to remember, which one of those letters means what? Right here, it says angular velocity. And right after it, there's the W-looking thing, omega. This is trying to tell you that this is the symbol for that. Down here, you've got alpha, right after where it says angular acceleration. So this is trying to tell you that this thing is the symbol for that. And so take your time, use the assets that are available to you, like the formula sheet, and match up. I got to find the same page again. Almost. That's where we were. Match up the numbers with the letters, you know, write it all out on paper and be methodical about it, just like in section 1. And that's how you should approach a question like number 5 here. So pause it here, do number 5, and while you're working on it, I'll get out of the screen share. Okay, unpause. So it says a wheel is originally turning at, or that's telling you how fast it's turning. Remember this little list I gave you back on the previous page? Well, you don't have a list exactly like this on the formula sheet where you can look at it on a test, but at least when you're doing your homework or trying to work on a lab or something, how fast is the angular velocity? So that's the symbol that goes with that 50 revolutions per minute. And since it's originally turning that fast, that makes it the initial angular velocity. Because, you know, just like in section 1, you've got initial, final, and average, and you don't want to be mixing them up with each other. So omega initial equals 50 revolutions per minute. Alpha, the angular acceleration, that's 0.25 revolutions per second per second. Now, before I go any further, maybe you notice there's a problem. Just like since the first day of the course, your units have to be consistent with each other. Revolutions here, revolutions there, that's all right. But for time, minutes here, seconds there, they have to match. So you've got your choice. If for some reason you really like minutes, you could convert seconds to minutes and do it that way. But, you know, seconds is the preferred SI unit, so I'm going to take the minutes and change them into seconds. 1 minute, it's the same thing I did up here in the previous question. 1 minute equals 60 seconds, so that minutes cancel out. And this is 0.833 revolutions per second. Okay, so now the units match. Seconds here, seconds there. Finish reading the question. The wheel's originally turning at 50 revolutions per minute. Got that. Has a constant angular acceleration. The fact that the angular acceleration is constant tells you that this group of equations will be valid. If the acceleration was changing, life would be harder. But these would not work if it wasn't a constant acceleration. So we got the 0.25 written down. Find how far it turns in 4 seconds. How far? How far is theta? So find how far it turns. Delta theta is actually the way it's written in the question. In 4 seconds. Well, seconds is a unit of time. So that's t equals exactly 4 seconds. Okay, So now that you've got all that organized on paper, the next thing to do is to, and this is on the formula sheet. So like if you're taking a test, you'd find these on the formula sheet, and you look for an equation that contains just the four things on the list. Well, for example, this one over here is no good. That's got omega final in it. I didn't write down omega final anywhere. And there's similar problems with the other ones. But this one here, I know everything except delta theta. And delta theta is what I'm looking for. So that's the way to go. Let's write it down. Delta theta equals omega initial times t plus 1/2 alpha t squared. Omega initial 0.833 times 4 seconds. Revolutions per second times seconds will give me seconds. Alpha is 0.25 times squared. Revolutions per second squared times seconds squared, because the unit gets squared along with the 4. That'll give me revolutions also. When you add numbers together, the units have to match. Revolutions plus revolutions. And it comes out 5.33. And so that gets us to the bottom of that page. And when you turn the page, top of the next one, it says section 8. So this is where I stop for today. Have a good however long until the next time we run into each other.